Hey everybody, welcome to lecture 5.3 on normal equations of planes. So far we've been studying vectors in multiple dimensions, usually dimensions 2 and 3, and later we're going to start applying some calculus techniques to this setup. But for now I want to talk about one last geometric concept, which is another notion of an equation for a plane called the normal equation. This equation only makes sense in 2 and 3 dimensions, and really in 2 dimensions it'll be an equation for a line, not a plane. But we'll study the line and plane equations, the normal equations for these things, and we will learn how to give equations for planes using normal forms or normal vectors. And we'll also understand why this is an important alternative way to write down a line or a plane equation. And mainly we'll use it to compute distances in the xy plane and in 3 dimensions. So this is the utility of a normal equation. One of the other nice things about normal equations is they're just easy to write down and easy to work with. So even if you're not trying to compute distances, these are good to know about. Just as a preview, we will also be using these to find tangent planes to surfaces described by some multivariable function. So the calculus is still to come, but let's just talk about planes for now. And before we even get into normal equations for planes, if we go down to 2 dimensions, we actually already know a notion of normal equation for a line. And I'll say, sort of without explaining it too much, that the equation, or any equation of the form 2x plus 3y minus 12 equals 0, or more generally, ax plus by plus c equals 0, is a normal equation for a line in 2 dimensions. You can see that this is not a function y as a function of x. This is an implicit equation of x and y. It describes a line because if we solved for y, for example, we would get something like a point slope or a slope intercept form for the equation, or rather for the line. And I've drawn a picture to sort of illustrate what's going on in terms of normal equations. So let me say a little bit more. If you look at the coefficients of x and y and pick these out and write them as a vector 2, 3, you'll see that this is exactly the vector drawn in purple in the diagram, whereas the line is drawn in blue. And if you believe the picture, if it's drawn to scale, this looks like it's perpendicular to the line. So this is our definition of a normal vector. A normal vector is one that is perpendicular to whatever set you're looking at. In this case, a vector is a normal vector for a line if it is perpendicular to the line, or equivalently perpendicular to any vector that lies on that line. And suggestively, if I have a formula of the form, or an equation of the form ax plus by plus something equals 0, then the a and b coefficients in front of x and y will always give us a normal vector. And by stretching n or reversing it in the other direction, we can find all possible normal vectors. And in 2 dimensions, they form a line's worth of vectors, exactly the line of perpendicular slope to our original blue line. So in 3 dimensions, we don't have normal vectors to lines. Instead, we have to go up a dimension in complexity and look at planes. We know a few different ways of writing down planes, namely by specifying a point on the plane and then either 2 other points or some vectors in the plane, and we can write out an explicit formula for that plane like we did 1 chapter ago. But in 3 dimensions, the nice thing about having only 3 dimensions to work with is once we've specified 2 of those dimensions or directions for the plane, there's only 1 more direction to use up. And that is completely described by a normal vector up to rescaling. So if you have a plane in 3 dimensions, there are normal vectors to that plane, and they are all parallel, or they all lie along the same line. This is really a theorem coming from 3-dimensional geometry that we're not going to prove. You can use linear algebra to prove this rigorously, but we'll take this on faith that every plane in 3 dimensions has normal vectors, just like every line in 2 dimensions has normal vectors, and here's one of them shown. The question now is, how do we find a normal vector given whatever input information we have about the plane? And here's the useful theorem that we'll just sort of use as a definition of a normal equation, although it really is a theorem that this works. And so I'm going to show you the formula, and then I'll explain what it means. So the normal equation of a plane in 3 dimensions can be written in 2 different ways. These are really equivalent formulas, either as a dot product equation, where we take the vector r minus r0 and dot it with n, a normal vector, and set that equal to 0. Or if we write out explicitly what the vectors r and r0 are, then we'll have, and take the dot product with n, we'll have a times x minus x0 plus b times y minus y0 plus c times z minus z0 set equal to 0. Now, I haven't explained what all of these pieces mean, but I just wanted to show you directly what a normal equation looks like so that you start thinking about what form it takes and how to recognize it in the future. We will typically use this form of a normal equation going forward. And if I had a 1 for c and I moved the z stuff to the other, or maybe a -1 and moved the z stuff to the other side and let a and b be written mx and my, what this would look like the multi-slope formula that we've had for a plane in 3 dimensions in the past, where mx and my are those slopes in the x and y direction. This is a little more general because I don't have to have this solved for z or written as z minus z0 on the other side of the equation. So this is even more general, and this can include the types of planes that are vertical that we weren't able to handle with mx and my previously. So let's go back and study each piece of this equation, starting with the dot product equation. Let's suppose we have a plane and we want to write down a list of all vectors that are perpendicular to that plane. Well, we know that if we can write down a vector in the plane, then any vector perpendicular to the plane will have to be perpendicular to that vector. And if we phrase things that way, it becomes a little more clear how to write this algebraically. Given a vector in the plane and any normal vector, let's call the normal vector n, with coordinates a, comma b, comma c, whatever that vector is, the two vectors being perpendicular or orthogonal means that their dot product is 0. So now let's take a step further back and ask how to write down any vector in the plane. Well, let's suppose we're already given a point. We're going to call that R0. And I'm writing this in the theorem using vector notation with angle brackets, but you should think of this as the tip of this vector, which is just a point in 3 dimensions with x0, y0, and z0 as its coordinates. Given that known point on the plane, any other point on the plane can be described as r with some coordinates, and then any vector on the plane. So let's say the coordinates of r will be x, y, and z, and then any vector in the plane can just be the displacement vector between our known point r naught and our other point r, whatever it happens to be. So any vector in the plane can be written of this form. And if you take a vector in the plane and take its dot product with a normal vector, you should get 0. They're supposed to be perpendicular or orthogonal. Furthermore, if we expand out what this displacement vector looks like, r minus r0 as a vector is going to look like, well, in coordinates, it'll be the x coordinates subtracted, it's the displacement vector, the y coordinates subtracted, the z coordinates subtracted. And when we take the dot product with n, that just puts an a, a b, and a c in front of each of these coordinates. And if we set it equal to 0, we get this form of the normal equation. Okay. There's a third way to rewrite this, maybe a fourth way if you believe the mx my version is equivalent, which is just push all the constants together into a single constant z, and then just have coefficients a, b, and c in front of our 3 variables x, y, and z. Okay, so we spent a lot of time on this slide, but I really want you to get comfortable with normal equations because we're going to start using them to compute things. By the way, this extends to higher dimensions. We already saw that a normal equation in 2 dimensions describes a line. And the normal vector in that case is a comma b. That's always orthogonal to the entire line. In 3 dimensions, a normal equation defines a plane. And in a higher number of dimensions or high number of variables, we have something that looks like constant times x1 coordinate minus coordinate of some known point plus constant times the same thing for the second coordinate up to however many coordinates we have, and set that equal to 0. This defines something called a hyperplane, which is the analog of a line or a plane in higher numbers of variables. Notice that each of these are set equal to 0 and they don't have a d, a c term or a d term here. We can actually take any of these lines, planes, or hyperplanes which pass through the origin and translate them by some value c or d, or in this case a n plus 1, and that will give any line, plane, or hyperplane in any number of dimensions passing through any point that you like. Let's work out an equation for a normal equation for a plane given 3 points. And in this case, we'll take the 3 points to be the intercepts with each of the x, y, and z axes. And as with many mathematical situations, we might be given different types of information to start our problem. So a plane in 3 dimensions can be specified by just knowing 3 points on the plane, as long as those 3 points are not in the same or lie along the same line together, which these do not. They lie on 3 different axes. But we know that the form that we're looking for in this case is some normal equation of the form ax plus by plus cz plus d equals 0. And I've rewritten things to just pick off the 3 coefficients a, b, and c, and then separate all of the other constants into our constant coefficient d. The normal vector here then will definitely be those 3 coefficients a, b, and c thrown into a vector. So all we have to do right now is determine what a, b, c, and d are. Hopefully we can find all 4 of them using our known information of 3 points that lie on the plane. Well, for the first point, 4, 0, 0, if we plug those in for x, y, and z, we'll get 4a plus 0b plus 0c plus d is equal to 4. And if we solve for it, well, I see that d is easy to solve for. So if I write this in terms of d, this will say that d is equal to negative 4a. So this doesn't completely solve for a, b, c, and d yet. Of course, we didn't learn anything about b and c, but we at least have some information we can hold on to for the moment. I need to keep my points on the picture. So now let's plug in 0, 3, 0. We'll get 0a plus 3b plus 0c plus d is equal to 0. And if we solve for, let's solve for d again, this might be useful. We'll get d is negative 3 times b. So whatever a and b are, we know that d is negative 4 times one of them and negative 3 times another of them. The last point we plugged in, or we're going to plug in, is 0, 0, 8. So let's do that one now. 0a plus 0b plus 8c. And notice that these 3 intercepts are each giving us different information about the 3 coefficients a, b, and c. So if we solve for d, again, we'll get negative 8 times c. And that's actually all the information we have. Notice that I could choose values for a, b, and c. I can't choose anything I want for a, b, and c, but of course we know ahead of time that we're expecting a single normal vector direction, and then we can scale to get all the possible normal vectors. But if we choose a value for d, we can actually solve for a, b, and c by unraveling these equations, and any value of d will work. This reflects the fact that there are infinitely many normal vectors, but there's a single one up to rescaling. So let's go ahead and just choose some number d that satisfies all 3 of these equations. D needs to be, looks like a multiple of 4, a multiple of 3, and a multiple of 8. The smallest number I can think of that does that is 24. And just to make the minus signs work out, let's just go ahead and choose d to be equal to negative 24. And in that case, let's write out what a, b, and c have to be. If d is negative 24 and d is supposed to be negative 4 times a, then a is going to be 6, b is going to be 8, and c is going to be 3. And you can double check that my equations are satisfied. You can also double check that once we choose these values for a, b, c, and d, and we get the equation, the normal equation then is 6x plus 8y plus 3z minus 24 equals 0. You can now check that each of the 3 points, those 3 intercept points we chose, satisfy this plane equation. We also wanted a normal vector, so let's write down what the normal vector is. It's just throw these coordinates a, b, and c into a vector: 6, 8, 3. And by construction, really by the theorem that we saw in the slides, but the way that we've set up our normal equation situation, this is perpendicular to every vector in the plane, and therefore it's perpendicular to the entire plane. So there we go. That's our first normal equation. How did that feel? Let's press on and see what else we can do with these. Let's go back to 2 dimensions and think about how we can use normal vectors and ultimately the normal equation to find distances in 2 dimensions. We're going to do this in 3 dimensions ultimately, but I want to pare things back to 1 dimension down so we can understand things better. So let's look at our picture of the same line from before: 2x plus 3y minus 12 equals 0. This is a normal equation for a line in 2 dimensions. The normal vector here again is 2, 3, and a known point on the line apparently is 3, 2. You can double check this by plugging it in, or you can believe that the picture is accurate. So given our known point 2 comma 3 and our normal vector, our known point 3 comma 2 and our normal vector 2 comma 3, we can ask about distances from points to the line. For example, if we look at the points 7 comma 2 and 4 comma 0, can we find what the distances are from these points to the nearest point on the line? We'll do that in a moment. And also, can we determine more geometric information, such as which side of the line do these points lie, without necessarily having a picture in mind? So I'm going to switch over to the tablet and work this out with you. I want you to be thinking about all the possible geometric questions we could ask about this situation, and then how it's going to work in 3 dimensions eventually. So we have a normal equation for our line. We have a normal vector in particular, and a point that we know. And for the moment, let's plot the points P1 and P2 before saying anything else. So 7 comma 2 is right here. Here's P1. And then 4 comma 0, that's the other point we're looking at. That's P2. And part 1 of the example asks us to draw the vectors starting from P and going to each of those points. So P, by the way, 3 comma 2 is right here. And here are our 2 vectors, P to P1 and P to P2. So I want to point something out before we do part 2 of this example, which is if we wanted to compute the distance from the point P to the point P1, or from the point P to the point P2, we have a distance formula already, so we don't need anything about the line or the normal vector. But instead, if we wanted to compute the shortest distance, maybe that's not quite the right angle. We want to compute the shortest distance from the line out to the point. We want to construct a right triangle and compute the hypotenuse, again, is the length of that vector from P to P1. We want to actually compute the length of this leg of the right triangle. And similarly for P2 back to the line, we'd want to compute the hypotenuse of, the shorter leg of this triangle. And that'll tell us the shortest distance from point to line. This is really an optimization problem you might have learned in Calc 1. And we can do this essentially using just vectors and no calculus at all. It'll just be in terms of dot products and lengths of vectors. We'll see that formula in a moment, but this is the type of problem that we can use normal equations to solve. For now, let's do the related geometric question of, without a picture, how can we tell algebraically, using apparently the dot product, which side of the line P1 and P2 lie? And here are the key pieces of information we need to solve this geometric problem, number 2 in the example, which is that vectors on the same side of the line as our vector n that we've drawn, our normal vector, are going to form an acute angle with n. Namely, there's only a range of possible angles for vectors that lie on the same side of the line, namely our green vector from P to P1 that looks like it's on the same side of the line as n. And for any of these angles, or any of these vectors, you can see that the angle will be an acute angle with n. Or in other words, it'll be at most 90 degrees or pi over 2 radians. On the other hand, if we extend vectors in the other direction or on the other side of the line, they'll have to form obtuse angles. And the real algebraic trick here is knowing how the dot product keeps track of acute versus obtuse angles. And if you remember from our lecture on the dot product a couple lectures ago, the dot product is positive if the angle between the 2 vectors is acute, and the dot product is negative if the angle between those 2 vectors is obtuse. The dot product, by the way, is 0 if they form a right angle, which would happen if our point actually was in the same direction as n when we start n with its tail at P, which doesn't happen in this case. You can see the points P1 and P2 are in different locations, but that's the idea. So let's compute these dot products and see if they give us obtuse or acute angles. For n dotted with P to P1, we need to go back and look at our normal vector n. That was 2 comma 3. And we want to dot this with the displacement vector from P to P1, which we actually didn't even compute. But since we have coordinates, we can do this quite easily. P1 is 7, 2, and P is 3, 2. So I want to take 7, 2, and subtract 3, 2 from it. So let's simplify before we take the dot product. The displacement vector is then 4, 0. And let's double check geometrically. Does this make sense? Yeah, it looks like it moves 4 units to the right. Here's the vector we're looking at right now. And 0 units up or down. So that's our displacement vector for P1. And we want to compute this as a dot product. So let's dot the coordinates. That'll be 8 plus 0, which is 8. 8 is positive, and we don't have to do any more. This shows that the angle is acute, and therefore this point is on the same side of the line as our normal vector is pointing. So that's interesting geometric information. And again, we didn't need the picture up above. All we had to do is be able to write down the components of these vectors, take the dot product, and check if it's positive or negative. Let's do the same for P to P2. So the normal vector again is 2, 3. And in this case, we're going to have something minus 3, something minus 2. Let's go check what P2 was in coordinates again. P2 is the point 4, 0. So to simplify, the normal vector is 2, 3. The displacement vector is 1, negative 2. We take its dot product, that's 2 times 1 plus 3 times negative 2. That's going to give us, let's see, 2 minus 6 is negative 4. Negative 4 is negative. And this tells us we have an obtuse angle, or in other words, the point lies on the opposite side of the line from our normal vector that we've drawn. So there we go. We're going to do distances next. You can probably see it at the bottom of the screen, but let's build up to that. And by the way, this same trick works in 3 dimensions. If we, instead of a line and different sides of the line, if we have a plane and a normal vector for that plane, we can compute dot products of displacement vectors from a known point on the plane and dot it with the normal vector to decide if the angle is acute or obtuse. This is going to tell us in general if points lie on opposite sides of a plane in 3 dimensions as each other. And I would say that's actually really powerful. I don't know a really efficient way in general. I know the brute force way of just trying to plot the points or computing displacement vectors from the nearest point on the plane, but I don't know a really efficient way of just quickly testing which side of a plane in 3 dimensions a given point is until we know this dot product trick. So we'll be able to do this in the classwork for a 3-dimensional example, but let's move on and talk about distances. So there's a proof of this in the book, or there's at least a quick sketch of the proof. But I want to just cite it as state it as a theorem that will allow us to compute distances efficiently. So if we have a line, a plane, or a hyperplane that has a normal equation of the form, some linear expression, a1 x1 plus a2 x2 plus all the way up to the number of variables is set equals 0. And if we know a corresponding normal vector, which in that case would have been a1, a2, all the way up to ak, then the distance from the hyperplane to a given point q1 through qk in that k-dimensional space, treated as a signed distance, so keeping track of if it's a positive or negative value, is given by this formula. And in words, we plug the coordinates of q into our normal equation, and then we divide by, this actually is a typo, this should be the length of the normal vector n. We'll do this together in a moment, but I want to just do a quick gut check that this works in this picture. If we have, and actually I'm going to switch back to the picture we had before. So if we had a point and we drew the normal vector from the nearest point on the line out to that point, this was our Q, how would we compute the distance? Well, it would be the length of that normal vector. And in this case, I mean, the normal vector is always already given to us in the picture, but if our normal vector instead were a different length, starting from the nearest point going out to P1, or the same thing for P2, how would we compute the length of that vector? Well, it involves the projection formula. The scalar projection times the normal vector will give a vector of the correct length. And if you carefully look at the scalar projection formula from our video on the dot product, you can rewrite it in the following form. And we'll do an example, but I just want to show you the formula with the length in the right place. So it's going to be plug the coordinates of our point into the linear form L of x, y, z, or L of any number of variables that describes or that gives the normal equation of the plane or the hyperplane, and then divide out by the length of the normal vector in order to get a vector of the correct length. So this distance in general is a signed distance. And if you only care about the true distance, you can take an absolute value at the end. So let's do this as an example. Let's compute the geometric distance. And when we say geometric, it's another way of saying signed. So keep track of the sign of the distance. Keep track of the direction the vector is pointing. The distance from the origin out to the plane with this normal equation, 6x plus 8y plus 3z minus 24 equals 0. So you can double check that the origin is not already on this plane. If you plug in x, y, z equals 0, then we'll get negative 24 equals 0. That's invalid, so the origin is not a point on this plane, and therefore it has some positive distance to the nearest point on this plane, which we can compute using this distance formula. So this is a reminder of what the distance formula is. In order to compute it, we need to write down each of the two pieces. One is, what is the linear form L of x, y, z? In this case, we, just as a reminder, we want to plug in the point to compute the distance. So we'll end up plugging in 0, 0, 0. This is actually a function that works for any x, y, z point anywhere in 3 dimensions to compute its distance to this particular plane. So the linear form here is just the left side of our normal equation. So it's 6x plus 8y plus 3z minus 24. I want to have all of the pieces there. It's the thing that's set equal to 0, in other words, in the normal equation. The normal vector, we can pick off the coefficients 6, 8, 3, and then we can compute the length of this vector and ultimately plug things into the distance formula to get what we want. So the length of this vector is going to be the square root of 6 squared plus 8 squared plus 3 squared. And let's see, this is the square root of 36 plus 64 plus 9. You do a little bit of mental math, you'll get the square root of 109. I don't think that factors any further, but that's good enough. That's what the length of this vector is. Now to compute the distance, we're going to plug in the origin, but we could do this for any point, keep in mind. Divide by the length of the normal vector. And if we plug in 0, 0, 0, as we said, we'll get negative 24, that equation, divided by square root of 109. This gives us a signed distance. And then the true distance is just the absolute value of this number. So we only care about the length of the line segment from nearest point on the plane to the origin, then it's the positive number 24 over square root of 109. There we go. We've got a couple more things to wrap up. This is how we can compute distances using that theorem, using this distance formula. All right, there was the example we just did. I want to talk about a particular application of these, which is useful in a lot of different sciences that are mathematically based. And machine learning is a fancy way of saying handling some data and having a computer learn from data sets to distinguish between different states or distinguish between different pieces of information in the future. So this is machine learning really in a super basic nutshell. We're not going to go too deep into this sort of thing in this class. But for an example where a computer might be able to distinguish between states, we might train a computer on images of cells and train it to distinguish between cancerous cells and benign cells, or cancerous tumor cells and benign tumor cells. These are not just any type of cell in the body, but we'll want to train a computer to distinguish between these in order to predict if a particular cancer is malignant or benign. So in order to train a computer system, in order to perform machine learning in a really basic sense, we give the computer system a large set of cases, which really means a large set of pictures, along with the information attached to each picture of whether that tumor is cancerous or benign. Each case is going to be measured in a few different ways, such as the size of the tumor, the location of the tumor, and then some other things about the patient might be involved, such as the age of the patient, results of certain blood tests that were performed, and ultimately the numerical data that the computer will be looking for specifically will be the brightness of each pixel in a CT scan or an MRI scan, which is provided as just an image, a pixelated image that the computer can learn from. So each data type is given by a different dimension. We can think of brightness as a one-dimensional measurement of each pixel, but also the size, location, age, result of all these blood tests allows us to attach even more information in a high degree of complexity to the training data for this machine learning system. And we can also think of each case or each picture plus extra data that we feed the computer as a point in a very high dimensional space. And now the question is, can we use machine learning, or rather, what would a potential machine learning system do in order to decide if a future picture, a future piece of data that we furnish the computer system with is corresponding to a malign or a malignant or a benign tumor cell? Well, one way that a machine learning system is going to do this is by trying to fit planes or hyperplanes in higher dimensions through the given training data, and do so in a way that most accurately separates the two different states, or all of the cases, into either malignant or benign tumor cells. Let's just say that the red data points are pictures with extra data that correspond to the malignant tumors, and the blue ones are the benign tumors. So the computer is going to actually perform something like an approximation scheme or an interpolation scheme to draw the best plane through this data that separates the data into the two pieces. And if we're talking about a plane, and in higher dimensions, it'll be a hyperplane, the most efficient way to encode a hyperplane is through a normal equation. And that will rely on knowing a point in that hyperplane, and then a normal vector, which is perpendicular to the rest of that hyperplane. Knowing that information, we can then decide how far a given point is from the plane and what side of the plane it's on, using the two techniques we've developed in this lecture so far. And that completely distinguishes both how accurate the read of whether or not that point is malignant or benign, and well, first and foremost, which side of the hyperplane will tell us which state we're in, if it's a malignant or a benign tumor cell, and the distance from the plane will also tell us how accurate that read is. Points further from the plane are more likely to be, or are have a higher degree of certainty that they are that one particular type, and the plane is going to slice through points, or is going to slice potentially pretty close to points that are maybe harder to distinguish if the brightness distinction between malignant and benign tumor cells is not as clear. Then those types of pictures will show up closer to the plane. That was probably a lot of information, a lot to wrap your head around, but I just want to bring things back to the original questions we're asking about lines, planes, and hyperplanes, and how their normal equations help us study them further. So the first review question is, what information do you need in order to write down the normal equation of a plane? And if you think about it in different dimensions, what information do you need to find the normal equation of a line or a plane or a hyperplane in any dimensions? How are the normal vectors of a plane all related to each other? For a single plane, we have infinitely many normal vectors, and there's a certain way that they relate to each other. Next, if we write down a normal equation of a plane, what's the significance of the coefficients in this normal equation? And finally, how do we compute the signed distance and ultimately the true distance between a point and a plane? Here's one problem that we'll do together in the classwork, but you can work on this on your own before coming to class. If two planes are perpendicular, we can tell that that's true if their normal vectors are orthogonal or perpendicular to each other. And here are two planes that we can test this out on. Are these two planes perpendicular? And then there's a follow-up question B about general planes that are perpendicular and what we can tell about vectors in those planes. So that's it for the video. Thanks for tuning in, and I will see you next time.